So welcome. So in my last video, we have considered the classification of states in terms of communication relations. But in this video, I shall cover the classification of states as per the transient and persistent state. So let us start the classification of states. This is as transient and persistent states. Suppose a system starts from the state J. Now define f j k n be the probability that starting from state J, the system reaches state K after n transitions. That is at nth step for the first time. So that is the system starts from Jk and reaches the state K at nth step. That means these are the intermediate states. These are the intermediate states, and these are not equal to K. These are all the states which are different from K. So that means the system starts from the state J and reaches state K at the nth step for the first time. So next we have the probability P jkn. This is the probability that starting from state J, the system reaches the state K after n transitions. That is at nth step. So this is not necessarily for the first time. That means the system starts from the state J and reaches state K at nth step. So here, before reaching state K, already n-1 steps covered, and in between K also, the system may also comes through the state K or may not. So that is the difference between the pjk and fjk. So pjk, so starting from j, the system reaches k, and these are the intermediate states. There may be k is in between, and but fjk n, so starting from j to k, so intermediate steps, these intermediate steps, these are different. These are different from state k. So nth step, k is for the first time. Here k is not necessarily for the first time. So that is the difference between pjk and fjk. So now let tau k be the first passage time to state k. That means the number of transitions required to reach state k for the first time, starting from any state. So now tau k, this will be equal to minimum of n greater than equal to 1 such that xn equal to k. That means the number of transitions greater than equal to 1, so that at the nth step the system reaches the state k, and k, this n is the minimum value of n. Tau k is a random variable. The fjkn, since this is the probability that the system reaches state k starting from state j at the nth step, so this is the probability distribution. So fjkn be the probability distribution of tau k. Given that the system starts from state j. System starts from state j. Now we shall establish a relation between p jkn and fjkn. So this theorem is known as the first entrance theorem. So this is the theorem which gives the relationship between fjkn and pjkn. Now here, whatever be the states, j and k, we have pjkn, and this is equal to summation r equal to 0 to n fj kr into pkk n minus r, n greater than equal to 1. And here we have pkk 0 equal to 1, fjk 0 equal to 0, and fjk1 equal to pjk. Now we can state this theorem in another form also. Now this is p jkn. This is equal to r equal to 0 to n minus 1 fjkr into pkk n minus r, plus when r becomes equal to n, this is fjk n and pkk 0. So pkk 0 equal to 1. So this is becomes the relation. So n greater than equal to 1. Now here we can see, so pjk, let us understand this relation. So pjk n, that means this is the probability that starting from the state j, the system reaches k at nth step, not necessarily for the first time. So when the system starts, suppose j, and it reaches k at the rth step, suppose before n number of steps, it reaches the state k at rth step where r is less than equal to n. Then it remains there, that means in the state k, for remaining n minus r steps. So the first system starts from the state j and reaches k for the first time at r steps. So whose probability is fjkr. So once the system reaches the state k at rth step, it remains there for remaining n minus r steps. So this becomes the summation over all the values from 0 to n fjkr and pkk n minus r, n greater than equal to 1. So again pkk 0, the system starting from state k reaches again state k without any transition. That means the system is at state k. Since it is initially at a state k, so this probability becomes equal to 1. And fjk, starting from the state j, the system cannot reach another state k after 0 transitions, because when there is no transition, there is no change of state. So fjk 0 equal to 0. The system cannot go from one state to another without any transition. So system cannot go from state j to state k without any transition after 0 transitions. It is not possible. So fjk 0 equal to 0. And then fjk1, that means the system goes from the state j to state k after only one transition. So jk are different. So that means there is no intermediate transitions that is starting from the state j, the system reaches state k for the first time. So fjk1 that is also equal to pjk. So this relation is known as the first entrance theorem. So it gives a relation between the pjkn and fjkn. So let us start with first passage distribution. First passage distribution. So now let AFJKN, it is the probability that starting from the state J, system reaches state K at nth transition for the first time. For the first time. So now that means we define FJKN that is equal to probability that nth step the system is in state K and in between the intermediate step that is newest step, this is not equal to K because it reaches state K for the first time. So before nth transition the system was not in state K. So for all previous transitions mu equal to 1, 2 up to n minus 1. Given the system starts from the state J, so that means x0 equal to j. So similarly we have pjkn. This is the probability that at nth time, nth transition, the system is in state K and x new, this is equal to I is any other state. It may be mu equal to 1, 2 up to n minus 1, given x0 equal to j. That means the system starts from the state j. So this is the difference. X new not equal to k, this is here. That means at intermediate transitions, the system cannot reach the state k. Here this condition is not there. The system can go through the state k before n transitions also. Now let us define or denote fjk. So this denote the probability that starting with the state j, the system reaches state k starting from the state j, the system reaches the state k. So now Fjk, this will be equal to sum of all n equal to 1 to infinity. This is Fjkn. So this Fjk, it is the probability that the system starting from the state j and reaches state k. So when Fjk equal to 1, so suppose Fjk equal to 1, so that means it is the probability that starting from the state j, it is certain that the system reaches the state k. So that means starting from the state j, the system can definitely reach the state k. Whatever be the number of transitions be, but the system definitely reach the state k starting from the state j. So Fjk equal to 1. So that means starting from state j, the system reaches state k, this is certain. Now, in this case, so what is Fjk? So Fjk equal to, we have what is Fjk? Fjk equal to summation n equal to 1 to infinity Fjkn. This becomes equal to 1. So Fjk, this is the probability. These are the probabilities. So probabilities means total probability is equal to 1. So Fjkn, this n equal to 1, 2 up to so on. This is a proper probability distribution. So this is a proper probability distribution. This is a proper probability distribution, and this gives the first passage time distribution. This gives the first passage time distribution for k. Given that the system starts or with state j. So this is the probability. This is a probability distribution. So now, if this is a probability distribution, it has a mean. So if we define mu jk, that is equal to summation n equal to 1 to infinity n into Fjkn. So this is called as the mean or first passage. The first passage time, the average first passage time from state j to state k. So this is the average or the average of fast passage time from the state j to state k. So mu jk, this is the average number of transitions required for a state to reach state k starting from the state j. So provided the reaching state k starting from state j is certain. So in particular, if we take k equal to j, so in particular, if we take k equal to j, then what will be? Fjj n. So Fjj n equal to 1, 2, 3 up to so on. So that means starting from the state j, system can reach again state j, that means come back to state j at nth transition for the first time. So that means j here is a return state. That means starting from state j, the system definitely return to state j. So now this represents the distribution or the recurrence time. Recurrence means come back to state j. So this Fjjn, this will represent the distribution of the recurrence time of j, and if Fjj, that is equal to summation j equal to 1 to infinity Fjj n. If this is equal to 1, then it becomes a probability distribution. That means return, if this is equal to 1, so in this case, if jj equal to 1, then j is a return state. J is a return state, and since that is returning to state j is certain. Returning to state j is certain. So in this case, what will be the value of mu jj? So here the mean recurrence time to required to return to state j, mu jj equal to summation n equal to 1 to infinity n Fjjn. So this is the average time required for a system starting from the state j to return again to the state j. So this is called as the mean recurrence time. Mean recurrence time or state j. Mean recurrence time for the state j. So now there are some relations we shall derive. You can if Fjj equal to 1, that means starting from the state j, system can definitely return to state j. So return to the state J is certain when the system starts from the state J. So the state J is a return state. J is a return state or recurrent state. A recurrent state or a return state or persistent state. That means return to the state J is certain. Now suppose, now remark 2, if fjj less than 1, if aj jj less than 1, that means starting from the state J, the return to the state J is not certain. So here the state J is called as a transient state. Transient state. That means non-return state. Starting from the state J, it is not possible to return, or returning to the state J is not certain, it is uncertain. So if fjj equal to 1, the state J is called as a return state or recurrent state or persistent state. Now if jj less than 1, so then the state J is called as the transient state. So now remark 3, third. If mu jj equal to summation n equal to 1 to infinity n fjj. So this is the average recurrence time or average number of transitions required to return to the state J. If this is equal to infinite, then J is said to be a null state. That means starting from the state J, after infinite number of transitions, it can reach to state J. So that is the average number of transitions required to return is infinite. So J is a null state. So then fourth, if mu jj is finite, so that means the after a finite number of transitions, the system come back to state J, return to the state J. So in this case, J is a non-null state. Non-null state. So a state which is persistent, a persistent, non-null, and aperiodic. The period is equal to 1. Aperiodic state of a Markov chain is said to be an ergodic state. A state which is non-null. Non-null means Here mu jj is finite. Aperiodic, this period is 1. Then and persistent. Persistence means mu jj, this is equal to fjj equal to 1. So that is a persistent state. So a persistent, non-null and aperiodic is said to be an ergodic state. Now, in this case, suppose a state is a state but is such that we have pjk. It is the probability that starting from this state j, the system reaches state k after n transitions, not necessarily for the first time. This is equal to, we can write r equal to 0 to n fjk r. That means the system goes from j to k in r steps or r transitions for the first time and then remain there. pkk n minus r. So n greater than equal to 1, j not n, that we have already discussed it. Now here we classify a state as a transient or non-transient state, a persistent state. For a transient state, the return to the state j starting from the state j is not possible. But in persistent state, the system starting from the state j can come back to the state j definitely, certainly. So that is, we can classify a state according to a transient or a persistent state. Transient or non-return state, persistent means a return state, definitely return state. Now let us take an example. Now consider an example. Let xn n greater than equal to 0. This is a Markov chain having states s equal to 1, 2, 3, 4, 4 states, and with the transition probability matrix p equal to, so this is 1 by 3, 2 by 3, 0, 0, then 1, 0, 0, 0, then 1 by 2, 0, 1 by 2, 0, then 1 by 2, 1 by 2, 0, 0. Now this is 1, 2, 3, 4. This is also 1, 2, 3, 4. Now we have to classify the states of the Markov chain. Classify the states of the Markov chain. Now how we shall proceed? Now, basing upon this, let us first consider the transition graph. Now here, state 1. So starting from state 1, the system remains there, goes to state 1 in the next transition, this probability is 1 by 3. And it goes to the state 2, its probability is 2 by 3. Now, if reaches state 2, it come back to state 1 with probability 1. And then, suppose this is state 3, then from state 3, it goes to state 1 with probability half. And from state 3 to state 3, it remains there with probability also half. Then state 4 to state 1 with probability half, and state 4 to state 2, this is with probability half. We have to classify the states. Now we can see here that the system cannot stay in state 2, because once the system reaches state 2, immediately it goes to state 1. And here the communication between state 1 and state 2 is possible, but it cannot come to go to state 4 either from 1 or from 2 or from 3. So the system cannot return to the state 4. Again, the system cannot also come to state 3 from the states 1, 2 and 4. The system here immediately comes to state 1 from state 2, and the state 1 can be reached from all other states, from the state 2, from state 3 and also from state 4. Now let us classify with this idea. We classify. So let us consider for the first state, state 1. Now here state 1 and state 2 are communicable. State 2 can be reached from the state 1 and state 1 can also be reached from the state 2. So state 1, state 2 have same property. So we consider first state 1. So here F111. So starting from state 1, the system reaches again state 1 for the first time. Its probability is 1 by 3. Yes. This probability. Starting from state 1, the system. Starting from the state 1, the system reaches again state 1 in one transition. Its probability is 1 by 3. So now F11 in 2 steps. So here F11 in 2 steps. So 1 to 2 and then 2 to 1. So this will be P12 into P21. So this will be equal to P12. This is P12, so this is 2 by 3, and P21, so this is 1. So this will be 2 by 3 into 1. So this is 2 by 3. So now F11, 3 transitions. So F113, 3 steps. So 1, what are the steps? 1 to 2. Then suppose the system goes from 1 to 2. So from 1 it cannot go to 3. It cannot go to 4. So from 1 it will go to 2. And once it reaches state 2, it come back to again 1. So 1 to 1 to return, it requires only 2 transitions. So if it will take another transition, then it cannot come to state 1 for the first time. So F1 to 1, state 1 to state 1 at 3 transitions, but for the first time it is not possible. So this becomes equal to 0. So now, and this is again F11 also n, this is equal to 0 for all n greater than equal to 3. So now if you define F11, that is equal to summation over n equal to 1 to infinity F11n. So this will be F111 plus F112. So this will be equal to 1 by 3 plus 2 by 3. This is equal to 1. So we get F11, that is equal to 1. So if F11 is equal to 1, so then state 1 it is a return state. State 1 it is a return state. Returning to the state 1, starting from state 1 is certain. So that means state 1 is also called as return state, means persistent. So state 1 is persistent. Now we shall find the mean recurrence time. What is the average number of transitions required to return to the state 1, mean recurrence time. So for state 1, so that is equal to mu 1 1. So that is equal to summation over n equal to 1 to infinity n into F11. So that is equal to 1 into F111 plus 2 into F112 plus 3 into F113 plus up to so on. So this is equal to 1 into F11n. This is 1 by 3 plus 2 into this probability is 2 by 3. So this is equal to 5 by 3. So this is finite. So state 1 is non-null. So state 1 is non-null because this mu11 is finite. So now state 1 is persistent, state 1 is non-null. Now to find the period of state 1. Now if we see P11, P11 this is not 0, P11 equal to 1. So this is not equal to 0. If P11 not equal to 0, then state 1 is aperiodic. Now state 1 is aperiodic, non-null as well as persistent. So that means state 1 will be an ergodic state. State 1 will be an ergodic state. Now it is communicable state 1 to state 2. So state 1 to state 2, they are communicable with each other. So state 2 will also be ergodic because the states which are communicable with each other have the same properties. So since state 1 is ergodic and state 1 is communicable with state 2, so state 2 will also be an ergodic state. Now here I am finding for the state 1, but directly you can also find out for state 2 in the similar way. That means you can find for the state 2, you just find out F221 and F222, F223 and so on. Then you find the summation. You just proceed as in as per the state 1. So you can now verify state 2 is also ergodic as 1 and 2 are communicable. Now for the state 3. Now let us go for state 3. Now for the state 3, F331. So this is equal to 1 by 2. F332, that means in 2 stages. F333 in 3 transitions. These are all 0. So F33, that will be equal to summation over n equal to 1 to infinity F33n. So that is only equal to F331 because all other are 0. This is 1 by 2 less than 1. So state 3 is transient. Because starting from state 3, returning to the state 3 is not certain, it is less than 1. So state 3 is transient state. Similarly, we can also verify state 4 is also transient. So this is the way by which we can classify the states of a Markov chain. You can try another problem. So consider a Markov chain Xn with state space S equal to 0, 1, 2 and transition probability matrix P equal to 0, half, 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 0, half, 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 0. You can also classify the states of the Markov chain here. So you can take different transition probability matrix and in the similar way you can also verify the states of the Markov chain. Now hope you have all understood the concept of transient and persistent, and also you can able to classify the states of a Markov chain. Now thank you for your patience in watching this video till the end. So definitely you can be benefited from the and every time this classification of the states is important, because you can get similar the questions in CSIR, similar questions in RBI, and you can get similar questions in your GATE exam. So you can practice by considering different problems and you can classify. Thank you.